No shit. Oh, okay. 谢谢，谢谢，谢谢。Right. Time for today's class. Good morning, ladies and gentlemen. Good morning, boys and girls. Time for today's class. Hopefully, it will be a pleasant day. Okay. Now, in the beginning of this class, I have to tell you that I already updated this PowerPoint file. Okay. So please go to your Facebook group and download the newest version of our PowerPoint file. Okay. I'll keep updating it. I'll keep improving it. Okay. Hopefully, it will improve the quality of this course. Now, the first thing I want to do today is review X-domain session analysis. Remember that the goal of session analysis is that given the input is known, given the session is known, we want to predict the output. That is the principal goal of session analysis. Typically, we perform session analysis in time domain because that is what things happen. Well, right? Thing happens in time domain, okay? But by transforming the problem into S domain, the design and management of the system can become much less complex, okay? Now, let's go review what we have done in the X domain for system analysis. Here in this course, the systems being considered is this nth order so-called causal linear time invariant system. LTI stands for linear time invariant. Linear means here, this system, you don't see any coupling terms. You don't see any terms like square or cosine or sine like that. Okay? Now, so the principle of superposition is applicable for such a system. The reason why it is a time invariant system is because we assume all the coefficients here are constants. Okay? None of them are function of time. Okay? Now, this is a linear system. I mean, the equation, the differential equation itself represent the system. X, of course, represent the input, and the corresponding Y represents the output. So, mathematically, we want to solve these differential equations with given X. All right? So, in the area of mathematics, what system analysis means is solving differential equation for its solution. Here, we have two additional conditions. One is we have assumed m cannot be larger than n, okay? Where m is the highest derivative of the input, and n is the highest derivative of the output. And the second conditions are so-called initial conditions. We need to know that the initial values of y and y dot, and all the way up to y n minus 1 derivative. Now, we also want to define two polynomials. One is what we call characteristic polynomials, which is made of the coefficients of the the left-hand side of the ordinary differential equations. Also, we want to define P of X. Well, these elements or these coefficients come from the right-hand side of this equality, all right? With Q of x and P of x defined, okay, we can transform the entire equation, and the result of the Laplace transform can be written as this, all right? Now, here, in transforming these Laplace equations, we need to use this mathematical equality, which tells us that if I take Laplace transform of the case derivative of y, what I will get is, first, I need to have the Laplace transform of y, and then I times this y with a to k, I'm sorry, with s to k, all right? So the rule is very straightforward. You take the you take the Laplace transform of the case derivative of y. What you will get is you need to time y of x, which is Laplace transform of y of t, times x to k, all right? Now, if you think of it as if you think of this, the case, let me rewrite the case derivative of y as d to k, where d is what we call differential operator. Then you will see this is what we will get. All right. So the representation in the time domain and x domain are actually very, very similar. Actually, on the surface, on the appearance, they look. Here, the mathematical operation is differentiation. Here, the mathematical operation is multiplication, all right? But please keep in mind, this result is very on the right-hand side of this equality. In addition to this term, you also have a number of other terms which are made of initial conditions or initial values, all right? Now, by taking this Laplace transform, by taking Laplace transform of this differential equation, eventually what we will get is this. And if we solve for y, this is what we will get. And it tells us that the resulting y of x, which is the output, let me put it this way, which is the Laplace transform of the output of the system, actually consists of two parts. All right? The first part comes from the input. The second part comes from the initial conditions. What is I of x? I of x, it can be shown, can be represented as this equality, where phi of k of x here are given in this equation, all right? Now, apparently, I of x come from the initial conditions. So I of x here represent the overall contribution from the initial conditions. I of x represent the overall contribution of the initial conditions. By contrast, this term here represents the contribution from the input. Well, P of x have already been defined, and the ratio of P of x to Q of x is defined as transfer function, okay? This is very, very important, okay? Now, since the output is made of these two terms, so we need to study them one at a time. Why do we have to study them one at a time? Because they represent different stories. This is about initial condition. This is about the input, okay? So when it comes to the input, the response resulted from the input, we call it zero state input, okay? Zero state means zero initial condition. It is purely due only to input x of t with all initial conditions zeros. In this case, this term vanish, it goes away. Now, if we end the remaining terms, tell us if we want to determine y, all you need to do is multiply the Laplace transform of the input with transfer function. Okay, but again, the true goal here is to determine the output in the time domain. Why? Because that is what things are really happening. So what we need to do is take the inverse Laplace transform. What we will get? Well, H represents the inverse Laplace transform of the transfer function. And it is called the impulse response of the system. Okay, we will look into the impulse response very soon. Okay, and x is of course the input. All right. So the product of two functions, if you take the inverse Laplace transform of the product of two functions in the S domain, what you will end up with is the convolution integral of these two signals represented in time domain. Okay, multiplication in the X domain, these two convolution integral in the time domain. Now, when it comes to zero input response, we pretty much do the same thing. All right, and so the total response, as we expected, is made of zero state response and zero input response. Well, and here we define h of t as the impulse response, which is the inverse Laplace transform of the transfer function. And remember that if you know the differential equation, okay, then you know then you know the values of all these coefficients. Then you can determine Q of x and P of x, okay, without any difficulty. And then you can determine transfer function. And then you can determine the zero state response. All right? Then, now, this is actually a very important result and a beautiful result because it tells you that in the X domain, you can connect the interaction, you can connect input with output via a very straightforward mathematical operation, which is multiplication. And you learn multiplication in elementary school. So it is a very, very simple, fundamental mathematical operations. Everybody knows what it means by times let's say your input by a factor of 2 or 3, all right? And that's exactly what happened here. You have a very simple, very straightforward, very easy to understand connection between input and output. And that simple connection only appears in the X domain, all right? So with such a simple connection between the input and output, remember that the goal in control is to come up with a good input signal so that the resulting output conform to my requirement, conform to our need, right? We want to do something with our input. And the reason why we want to do something with our input is that we want to achieve something in the output end of our system, all right? So we need to know how input impacts output. And this simple equation tell us in the X domain, you can connect the relationship with X and Y by using a simple mathematical operation, by using multiplication. All right? I say the same thing several times. The reason why is I want you to learn it by heart. Okay? So let's review what we have learned. In control systems, the main focus is on improving the system output, but by manipulating the system input, because the input does not influence the initial condition, right? Initial condition is something pre-exists, okay? My input cannot do anything about it. So the Zell input response is generally not considered when designing control system, all right? So Zell input response is, generally speaking, not part of something we should worry about in designing a control system, okay? But nevertheless, okay, the Zell input response, nevertheless, is always a part of our total response. We cannot, we ignore, we don't do anything about it. It's not that it doesn't have any impact. It does. We don't pay any special attention to it in designing controller. Is because there is nothing we can do for this part of the response. Okay. All right. Unless otherwise specified, the term system output in this course refer to zero state response. All right. Keep in mind, most of the time we only consider zero state response. The transfer function serves as a fundamental mathematical model for control system design. Okay, keep that in mind. In X domain, transfer function represent the system. Okay, using the Laplace transform, time domain differential equations are converted into algebra equations in the X domain, providing a clear description of the input-output relationship. A clear description of input-output relationship. Okay, that's what it means. A key aspect of analysis is understanding how system parameters, such as order, pose, and Zell, affect overall system behavior. Why? Because they are all parts of the transfer function, and transfer function represent the system. If I want to understand the system, I need to have knowledge about Laplace transform. If I want to have adequate knowledge about the transfer function. Okay, if I want to understand the system, I better understand transfer function. If I want to have a good understanding of transfer function, I better have some good idea about its parameters, including order, pose, and zeros. All right. Now let's switch back. Let's now focus on zero state response. Actually, we talked about this at the end of last week's lecture, but I want to do it again, okay? Because it is important, because of its importance. And in particular, I want to emphasize the contribution of convolution integral for finding the result of zero state response. Okay, let's say this is my input, f of t, okay, for n-order linear time invariant system. Now, f of t here is a CT signal, which means it's a function of time or a continuous function of time. Now, let's take this signal apart, okay? Now, by approximate the area under the curve with a series of rectangles, okay? This is one of such rectangles. Now, the width of this rectangle is what we call sampling period, delta tau, and the height is precisely the value of the function. All right. So the next thing we assume is that, assuming that if this is the input of the system, then the output of system appears like this. So this is an impulse function. So h of t, by definition, is called the impulse response. Okay, so which means if I have a linear time invariant system, if I apply delta t to the system, and the resulting output will be h of t. Okay, and since this input is an impulse function, therefore, of course, this output will be impulse response. All right, because this is the result of delta t of the. All right, so if this is the case, let's just write this relationship as this mathematical equation: input, output. All right, now the next thing I do is I will delay the input by 就是慢一点而已。谢谢。所以我再分享一下荧幕 ，OK。All right. Finally. Okay. Okay. Let's come back to our lecture. Okay. It's very lucky that I have such a capable TA to help me resolve such a difficult situation. Okay. And should you have any question in this class, you can always come to see me. But if you prefer, you can always go to see the TA. He is very competent. And I'm very positive that he will be very helpful and very willing to help you. Okay? All right. Now let's go back to where we were. Okay? We assume this is the input and this is the output. So if the input is is an impulse function, and accordingly, of course, the output can be referred to as impulse response. The next thing we do is we delay the input by n times delta tau, all right? Okay. Originally, the input is applied at t equal to 0. Now, impulse function now is applied at t equal to n times delta tau. What will happen to the output? Since we are dealing with a time-invariant system, the impulse response, the resulting output, when it comes to the waveform, it remains identical. However, since I delayed the input by this much time, the output, the resulting response, will also be delayed by the same amount of time. So if this is the input, this will be the corresponding output, since we are dealing with a time-invariant system. And this result is also one of the very important property of time-invariant system. Now, the next thing is I want to times the input by this, okay? What is f of n delta tau times delta tau? It is actually the area of this rectangular. Where does the rectangular come from? This rectangular come from here. It is a piece, a part of the input signal. Remember now, what we are doing here is we approximate the area under the curve of f of t by the areas of these rectangulars, all right? Now, why do we want to do that, okay? Why can we times delta tau with the area of this rectangular? Because delta function itself is a signal of unit area. Okay, why? Remember the definition of impulse function. We assume originally this is what we have, okay? But if epsilon goes to 0, then this converted to so-called impulse function, right? No matter how epsilon is, based on the definition of this figure, we know that the area of these rectangulars is always 1, all right? Since the height is 1 over epsilon, and the base, the width of the base is epsilon. So the area is always times 1 over epsilon, which gave us unit area, okay? So impulse function represent a signal of unit areas, and what we have is not a function of unit area. It have its own size. So we just times the size, the area of that rectangular. all right? And since we are dealing with a linear system, the resulting output will have exactly the same structure, which means I still have the same H, since you still have the same delta. The only difference to go from here to here is the input times this area of this rectangular. And since this is a linear system, so the property of additivity, or let's jump directly to the principle of superposition is applicable. Therefore, I'm 100% sure this will be the resulting output, all right? Now, remember that what we have dealt with is just one rectangulars. So we need to consider, since we need to consider all rectangulars, because the sum of these rectangulars represent the signal itself. So what we need to do is take the summation, all right? And from minus infinity to n to positive infinity. For every given value of n, we correspond it to one piece of rectangular in this figure, all right? And the resulting output will be this, which means if you have multiple inputs, then I have multiple outputs, okay? Why can I do that? Again, because this is a linear system. Therefore, I am 100% sure that the principle of superpositions is applicable, okay? Now, if if delta, we can see from these figures that the area under the curve of F and the area, there is a difference between the area under the curve of F and the area of these rectangulars, right? There is always gap between them. Now, however, it is easy to see that if I reduce delta tau, then such a discrepancy will also be reduced. And if I push it to the limit, that is, if I make delta tau approaches 0, then such a discrepancy, such a difference will also converge to 0, okay? And that is exactly what we want to do. We just assume delta tau goes to 0. And mathematically, we can show that this will convert this summation into this integral, okay? And this integral, by definition, is nothing but f of t, which is the input, all right? We talk about that, all right? Because this is the result of the summation of all the areas of the rectangles. And when delta tau approaches 0, then the areas of all these rectangles is essentially the same as the area under the curve of f of t, right? And this, of course, is the resulting output, y of t. And this power of y of t is what we call zero-state response, all right? Now, before we rewrite zero-state response, let me first talk about the definition of convolution integral, all right? Now, here we have just shown that the state response of y of t of an LTIC, LTI, of course, represents linear time invariant. C stands for continuous, all right? Their state response is a convolution integral of the input and the impulse response of the system. Remember, impulse response is the inverse Laplace transform of the transfer function. Mathematically, this integral is the formal definition of convolution integral. The upper bound and lower bound are minus infinity and infinity respectively. Now, I want to revise the upper bound and lower bounds so that this convolution integral, this result of convolution integral can fit better with the zero-set response. Now, the first thing we do is we replace the lower bound by 0. Why? Because we are dealing with a causal system, because the input is a causal signal. T is defined as the time when control operation stop to take place. It's time of the initialization of the control process. Before T of 0, nothing happened. And the input before T equal to 0 is 0, all right? So f of tau is 0, okay? Since f tau is 0, when tau is smaller than 0, then there is no need to integrate this integrand from minus infinity, okay? You can integrate it from 0 minus, all right? And why? The next thing is h of t minus tau is 0 when tau is larger than t. Because if tau is larger than t, then h t minus tau for this part is negative, right? Which means you have a minus value inside the bracket, right? Now, h of t is 0 when t is smaller than 0. We know that. Why do we know that? Why do we know that? Because by definition, h of t is impulse response, okay? Where does impulse input starting to have an effect on the system? T equal to 0, right? Because that is the very time instant we apply the input impulse, all right? If this is the case, and if we are dealing with a real physical system, which are always causal system, then impulse response will, no matter what it looks like, it will only have value after t equal to 0, right? Because this the cause, this the effect. For causal system, effects is always come after the cause, right? Because here for causal system, output is always the consequence of input. This system has no memory, but I'm sorry, this system has no sense of anticipations, okay? Its output is always the result of the input. The output always happens after the input, all right? So if this is the case, we know that for linear time invariant system, this is always true. And if this is the case, we are pretty sure that when tau is larger than t, then h of t minus tau is 0. So we don't have to integrate this integrand all the way up to infinity. Or we can set up the upper bound to be t, okay? So what t is? T is the time variable, okay? That's it, okay? So after understanding the definition of convolution integral, there are here, what is given here is a convolution table, which means here is F1. Here, this column corresponds to F2. And the final column represents the convolution integral of F1 and F2. All right? So for example, if this is F1 and this is F2, the convolution of E lambda t times and the unit step function is this, okay? So which means you don't have to perform convolution integral operation by yourself. Whenever you need to do that, go to such a table to find the result, okay? Okay. If what you want is R not on the table, then their convolution integral probably cannot be derived analytically. All right. All right. So after understanding the idea of convolution integral, we know that the total response actually consists of these two parts, and this part is what we call zero-set response, which is the convolution integral of the input and the impulse function. All right. Now here the first term represent the input response, zero input response, where lambda. These lambdas are the eigenvalues or the poles of our system, and E lambda t represent a mode of our system. All right. Now, the convolution integral transfer the problem of solving the zero-set response of an LTI system into one of computing an integral or sum that is naturally parallelizable. What does that mean? Okay, when solving a differential equation using a computer, typically we have to do it one step at a time, which means I have to first, for example, determine what will happen in t equal to 1 before I can determine what will be the solution of the differential equation at t equal to 2. I have to do it one step at a time. It's very similar to that. If I want to predict the weather, let's say 3 days from now, the first thing I need to do is predict the weather of tomorrow and the weather the day after tomorrow, and then the weather after the day of tomorrow, right? Same thing happened to the numerical solution of differential equation, at least traditional numerical solution methods for ordinary differential equation. But with supercomputers, we have multiple cores. And therefore, to really accelerate the computing process, we need to parallelize our solution process. Now, how do we do that? Convolution comes in this case, convolution integral become a very convenient tool. Now, remember, this is the definition of the convolution integral of F1 and F2. And here, I assume the input is R, and G represents the transfer function of our system, and Y of t is the resulting output. And we all know that if OIK is the zero-state response, then the output is simply the product of the transfer function and the Laplace transform of the input. Let's assume RT to be an impulse function. And remember that if you take the Laplace transform of the impulse response, the impulse function, the resulting Laplace transform will be 1. Okay? This is actually a magnificent result, okay? Because in this case, when the input is an impulse response, the output will become nothing but g of x. Why? Because in this case, r of x is equal to 1. So the impulse response is simply the inverse Laplace transform of the transfer function, which is denoted as g of t, and it was denoted as h of t in previous slides. I apologize for the inconsistency of the samples because I wrote these notes at a different time of my life. So it's difficult to make it consistent since I use different tools. Now, and nevertheless, if y of x equal to g of x of Rx, and if I take the inverse Laplace transform of the product of g and r, this is what we will get. we talk about this. And we all know that this convolution integral can be written as this, okay? No big deal. Now, to determine the state response, what we can do is, if let's say, just directly use this result. Just directly use this result. How do I do that? For example, if I'm interested on the value of y at t equal to 1, all I need to do is set the value t equal to 1 in this convolution integral, which means that this t now becomes 1. Similarly, this t now becomes 1, and that's it. You can determine y1. And if you are interested in the value of y, or their state response at t equal to 2, all you need to do is replace t by 2. Okay? So you can do that in parallel. Okay? So you can, that which means that you can also determine the value of 3, y of 3, the value of y of 4, y of 5, all at the same time, provided that you have multiple CPU to help you do that. Or you have one CPU, but you have multiple cores, and one core take care of one operation. So that's the principle, that's the fundamental idea of parallel processing. And that is also one of the reasons why convolution integral is important, because with such a representation, with the help of convolution integral, you can solve the zero-state response of a linear time invariant system by using parallel processing power of a supercomputer. Okay? And that can make a difference. Now, let's emphasize the importance of the significance of the importance of impulse response. Significance, it provides a complete characterization of the system dynamic behavior. Why? Because impulse response is the inverse Laplace transform of transfer function, and transfer function represent the system model in the S domain. So in the time domain, h of t, the impulse response provide a complete characterization of the system dynamic behaviors, which means the impulse response fully describes the system behaviors. Now, why do I care about that? Okay, one of the very reasons why we think impulse response is important, because it can help us experimentally determine the model of the system. Remember that to model a system, we need to have a differential equations, right? Like this. Now, for a real machine, for a real system, which stand right before you, okay, how do you come up with such a differential equation? Let's say this machine is what I bought from Japan, okay, and I wanna copy that machine, all right? So my machine works exactly as the expensive machine I bought from Japan. But the first thing I want to do is I want to set that model, okay? Then for that machine, the first thing I want to ask myself is, where does this mathematical model come from?